Okay, hello everyone. Thank you so much for joining us this afternoon. We're here with Dr. Taylor. She's going to be going over some review materials for exam 2. If you have any questions, feel free to post them in the Q&A chat. But I'm going to go ahead and hand it over to Dr. Taylor, and we're going to get started.
Fabulous. Thank you so much. All right, it is Sunday, October 1st, which means exam 2 is right around the corner. So exam 2, to remind y'all, is going to be on Saturday, October 7th, 10 a.m. For those of you that took your exam with ARC, you guys will have a different time. I'll be sending those email reminders out this week, but everybody else will be at 10 a.m. You'll also be in the same rooms. So wherever you were before, you will be there again. I will actually go ahead and throw that up real quick. I'm going to scroll back through my old announcements because boom, there they are. So these are the exact same rooms as you had for exam 1. These will be the same rooms that you have for exam 2 and 3 and 4. We'll double check. Hopefully they're the same for the final. It kind of depends, but exam 1, 2, 3, and 4, all the same rooms. So wherever you were for exam 1, same place. So a little bit of background. As far as content goes, this is off of your syllabus. So this is chapters 4.6 to 4.7. Now, what's chapter 5 and chapter 6? It's whatever we covered in class. So there are some things that are in those chapters that we don't actually test on. So for example, out of chapter 5, we don't do lattice energy. It's actually kind of cool. I actually really like lattice energy, but it got the chopping block. And chapter 6, I actually would have to go back because I don't remember the things we don't do out of chapter 6 because I've trimmed that one so many times I've forgotten what else is in there. 4.6 and 4.7, these relate other topics to ions. Now, the interesting thing about this is there's going to be electron configuration of ions. So the odd thing with this is you do have to still remember your electron configuration. So what I mean by that is if the problem asked for the electron configuration of, well, let's just do fluorine, but the fluoride ion now. So our fluorine neutral atom is right here on the periodic table. And so we're still going to need to remember, I'll go ahead and use the helium noble gas shortcut, and then 2s, 2p. And if it was just fluorine, the atom, I'd have 5 electrons in my p subshell, but this has a negative sign, so I need to add one more. So if it was neutral, it would be the helium 2s2, 2p5, but this is negative. We are now doing the negative version, so this is now going to be 2p6 to reflect that one additional electron. Same general idea if I instead had chosen, actually we'll go ahead and do one of the ones nobody likes. I need to be nicer when I say that. We'll go ahead and do iron. So iron 2+. So we're going to still first think about the neutral form of the electron configuration for iron. So the neutral form would start us off with argon, and then 4s2, iron 1, 2, 3, 4, 5, 6, 3d6. But since we're going to go to the +2, we're always going to remove from the highest value of n. So my values of n, remember, are these big coefficient numbers, these big numbers here. So I have a 3 and a 4. I'm always going to remove from the highest value. So 4 is bigger than 3. So I have a +2 charge, so I need to remove 2 electrons. So therefore, when I'm looking for my 2+, I am going to remove my 4s electrons. So this is the one that usually people are a little bit forget that we did, which is you don't just look at removing electrons from wherever you would have last put them in. We do actually remove them from the highest value of n. And do remember that some of these rules that may sound arbitrary when you hear them, remember and realize that really what we're doing is we're trying to give y'all sets of rules that reflect nature. So this really is coming from when we see iron in the real world and we work with it in its different charge states, what happens to those electrons and how do they act and where are they most likely to be? So I know sometimes it may seem arbitrary, but really we're just trying to describe what we experience in the real world. So that's a little bit on electron configuration of ions. And this other one that's in, so my point in doing all of that is that you'll probably also need to refresh on electron configuration in general. So it is electron configuration of ions, but in order to get there, you'll probably need some of your electron configuration. Same game, the other thing in 4.7 is size of ions. And some of this is not so bad, but you may want to brush up / remember atomic radii or atomic radius trend, because we can do a variety of different things and either have you rank them or ask you which one is larger. But for the most part, when we're talking about this is to refresh and reflect that when you are adding electrons, your ion size will get larger. So if we're trying to talk about the difference between neutral and negative, my anion form, then this is going to be bigger because essentially I have the same number of protons trying to hang on to more electrons. So as my nucleus suddenly is trying to hang on to more negative stuff, I expect this to get larger physically in the real world. And so then we would expect the reverse or the opposite to be true. That if I'm trying to talk about sodium hanging out over here as an alkali metal, my neutral form of sodium versus sodium with a positive charge as a cation, my cation, since I'm losing an electron and I now have a nucleus that has the same positive charge, but now hanging on to fewer electrons, I would actually expect my cation to get smaller. So keeping in mind that we can also think about we can think about neutral sizes and how they might compare to each other, but especially thinking about cations and anions and what's going to change, how these things are going to change with respect to each other. So that's a little refresh on the stuff that we did back in chapter 4, because oftentimes the stuff right after the last exam is a little bit harder to remember. So the other fun game that I am very well aware of, so I know for some of y'all it has been a little bit of a surprise. I tried to warn my class, but I know we cover a lot of stuff in 50 minutes. So no worries if you didn't remember. But the different instructors do go through the material in different orders. So it is really likely, especially as y'all are putting questions in the chat, that some people are like, oh yeah, we totally covered that. And other people may be like, what are you talking about? That is very normal. Like I know, for example, I did all of the math stuff in chapter 5, like right after the first exam. And Dr. Diekman, I know, is lining up to do all of the math stuff next week because he hasn't done it yet. So I don't know where the other instructors are because Dr. Oshami and I usually chat about other things when we are passing. Dr. Wong teaches in the morning, so I actually don't see him very much. But I teach in the middle between Dr. Diekman and Dr. Oshami, so I usually see the two of them. So the two of us can chat a little bit. So let's go ahead. I do have 2 calculation questions that I did come prepared with So I will definitely do these at some point, whether it is in the near future or whether it is in a follow-up video. But I will definitely do these two at some point. But let's go ahead and see if there are questions in the chat at this point and see if there's anything really burning on people's minds at the moment. Otherwise, don't worry, I have stuff that we can do if not. So questions right now.
Hi, there are questions. So the first one is, what are the important exceptions we should remember, such as coin group and other shenanigans that occur? The second one is, can you go over Lewis structure? The third one is, are binary ionic compounds always neutral? The other one is, can you go over percentage composition? How can we find the valence electrons for transition metals? May you go over the meaning of resonance and bond order in Lewis structures, as well as how to draw the best Lewis structure? Should you please review drawing resonance structure and also important concepts about electron negativity? Thank you so much. Can you explain molecular mass versus formula mass versus molecular mass? Can you please explain the relation between electron negativity, polarity, and dipole moment? Do homonuclear polyatomic exist, such as ozone? Could you go over the reason why transition metals have Roman numeral? Also, which one should we look over? The other one is, do we have to know the coordinate Lewis bonds or Lewis acid and bases? Sorry if I spelled anything wrong.
No, you're doing great. You're doing great.
There is something new. Why are some elements allowed to have more than 8 valence electrons in Lewis dot model? I see 1,5 where one iodine bond with 5 chlorine. All chlorine has complete octal, but iodine would have 12 VE here. 10 from 5 holds and 2 over the valence electron.
Okay. Anything else right now?
How would polyatomic atoms be brought up to the test?
Okay.
Okay, there's another one. Can you explain naming the hydrogen names for acid and ions? Could you go over oxy acids and binary acids and hydrates?
Okay. Anything else right now?
This is it for now.
Okay. This is plenty to work with. This is fantastic. Excellent. Excellent. Okay. There's one person who asked about the thing I came prepared for. Fabulous. Okay, so most of these are dealing with Lewis structures, which is not a big surprise. So what I'm going to do is let's go ahead and do some Lewis structure stuff. Especially there's some of these I might need remembering on. So the question that was about important exceptions, I tried to write that one down as quickly as I could. I'm going to hope that this first question that we took, which was important exceptions, I'm going to hope that this is in reference to Lewis structures. If it's not within reference to Lewis structures, then please put it back in the chat again. Compounds always neutral. So some of these that I can do kind of quickly though. Actually, so I will get to Lewis structures really quickly. I'm going to try to answer some of these. So one of the questions was basically, are ionic compounds always neutral? So, and there's two different ways to look at ionic compounds always being neutral. So there's two main groups, which is one is assume yes, and then the other one is, oh, but not these. So So yes, so you are going to assume that these are neutral, because one of the things that we can do is we can tell you something like, hey, there's an ionic compound and your ionic compound contains potassium and sulfur. Tell me what this is. Give the formula. If it's a question like this, where all you really know is that you have these elements in it, you have a metal and a non-metal, which means it's ionic, and you're told to give the formula, and the only real way you can do that is if it is ionic. Here we are assuming that it's neutral. And really, for the most part, if it is ionic, as far as like, this is a thing where you have a positive thing and a negative thing coming together, you do get to assume that it's neutral. So if we're trying to talk about giving the formula for potassium and sulfur, the first thing I'm going to do is head to my periodic table. You're going to see me go to this thing a lot, which is normal, and this is definitely a time where we do this a lot. So I said potassium and I said sulfur. So potassium's hanging out in my alkali metals. So potassium is going to have a +1. Sulfur is hanging out in group 6A. So this is going to be a -2. So I would expect my potassium and my sulfur to come together with 2 potassiums and 1 sulfur. And this should just be potassium sulfide, because I have potassium in that alkali metal group. So yes, you can assume that all of those are neutral. Now, the one thing I was going to say with the except for when they're not, which is something you are also responsible for, but these are actually going to be less obvious, because these are charged, which is your polyatomic ions. The thing here, though, is that it's in the name, ions. So there is a list of polyatomic ions that y'all are responsible for the exam. We will not give them to you. You do have to memorize them. It's the table out of your textbook. It's in chapter 6. And the thing, though, is that those are, so there's a set list of them, but we can do things like just using the word phosphate, and you need to know then that phosphate looks like this. Now, the thing about this is that this is an ion, but there's no metal here. So one of the ways that, to me, this is still something worth mentioning in the conversation about ionic compounds that you do need to know, but these are something where it has a specific name, it has a specific meaning. But if this was paired up with some other metal, you would still then assume that the compound overall would be neutral. So for example, if we were going to say that we actually had something like magnesium sulfate, or sorry, magnesium phosphate. I drew phosphate here, we're going phosphate. I would assume that this is neutral. Now the phosphate part I know has a charge because I'm going to have my polyatomic ions all memorized. So I'm going to know that when they say phosphate, that means PO4 3-. Magnesium, I'm going to head to my periodic table for that. Magnesium is over here, alkaline earth metal. So it's in group 2A, so it's going to have a +2 charge. So then I can go ahead and put these two things together, and I am still going to assume that the overall thing has a neutral charge. So I guess the short answer really is yes, you would assume that all ionic compounds are neutral. I just did have to throw that part in about we do expect that you all know your polyatomic ions, and since they are themselves ions, they're not neutral. But all the compounds that are together, those are neutral. Someone else mentioned Roman numerals. So I didn't do an example of Roman numerals in here, but basically the way that the Roman numeral thing works is I pulled examples from so far group 1A and group 2A. Group 1A is always +1, group 2A is always +2. So those are not always because this is a freshman class and we thought that it would be easy on y'all. Those are always as in like, that's the only thing that those elements do. They're either neutral or my alkali metals are +1. They're neutral or my alkaline earth metals are +2. I mean, I guess you can sometimes force them to do other things, but in a stable world, they really don't. So when you just see them hanging around, those are their charges. So there's a small subset of, there's 4 others that do always have the same charge you're also responsible for. They are silver, with this +1, zinc and cadmium, which is +2, and aluminum, which is +3. This information, by the way, for those of you that are either like, how was I supposed to know that? In your textbook. Where did I put it? I don't really want to go digging through Alex. I'm going to cross my fingers that it's here. In your textbook, there's a flow chart for naming ionic compounds. Oh, thank goodness I did put it in here. In your textbook, there is a flow chart for naming ionic compounds. Subtitles. I have my laptop set up to do subtitles, which is great, except for right now. And what they have is it actually has a little flow chart on here, and it says metal cations has only one possible charge. Alkali metals, group 1A, alkaline earth metals, group 2A, silver, aluminum, cadmium, and zinc, the 4 things I just went over. These do not have Roman numerals. Everything else that has a metal does have a Roman numeral, all of the other ones, which for the most part is your D block, also some P block. Technically, if we did F block ones, if we want to talk about like a uranium salt for whatever reason, or a gadolinium salt, those would also have Roman numerals in them. So just to give an example of that, but those 4 exceptions I was talking about, silver, cadmium, zinc, aluminum, are hanging out in this flowchart thing, which is in your textbook. So they are not random. I did not make them up. They're in a couple places, but they're in the flowchart in the textbook. So for example, if I wanted to talk about something that has to do with lead is down here. It's in the P block. And I wanted to mention lead for chloride. Then what that 4 tells me is that 4 tells me the charge on lead. My chloride ion is still hanging out in my group 7A. So the chloride is still a -1. So if I was going to put this together, it looks like this. But the Roman numeral tells you the charge on the metal. And it's a lot easier to actually tell you when you do not need it, because the hard thing is you need the Roman numeral when you have something that has a variable charge, when it could have multiple charge states. But that's a lot of the periodic table. So it's a lot faster to tell you when you do not need the Roman numerals. And the hard thing is that a lot of times when we give y'all examples, that you actually see a lot in real life. Sodium and potassium, real cheap. So sodium and potassium, we tend to have a lot of those salts in the real world because sodium and potassium are pretty economical. So you wind up with them a lot in labs. Cobalt salts they're more expensive. So you just don't see them as often. But 1A is +1, 2A is +2, silver is +1, zinc and cadmium are +2, aluminum is +3. Everything else that's a metal, you have to name and tell me what the charge is in Roman numerals. What have I answered at this point? So we have talked about ionics, things always being neutral, and that's a yes. We totally talked about transition metals needing Roman numerals. That's good. I'll keep coming back to this idea of how are we going to use polyatomics in exams. I did, however, already give you one example of this, which is the fact that we can just name compounds and have a polyatomic ion in there, and you should know what it is. So very much like we could use chloride with a D, we could also use chlorate with a T, and you should still be able to answer the question. You should still know what that thing is called, all of those pieces and all of those parts. Okay, I'm gonna do, sorry. I don't know if anybody else's allergies are acting up, but mine certainly are. Naming stuff, I'm actually going to hold off until later for naming acids and oxo acids and hydrates, because those are ones that, out of all the things, are usually easier to do in a follow-up video. So that means I'm on to something easy. Valence electrons for D block. Valence. Whenever it says the word valence, whenever we want valence electrons, I don't care where they are. The valence electrons are always the highest value of N. I do not care where they are. I do not care where they are. So let me actually take this to actually, I'm going to bring the periodic table to this. I'm using the periodic table so much today. I mean, and I should really know better. You'd think. So valence electrons are always going to be the highest value of N, and I do not care where you are. So let's just talk about, I'll talk about phosphorus. Why not? Phosphorus. Neon, 3s2, 3p3. Valence electrons is highest value of N. That's everything in the p subshell. Phosphorus should have a grand total of 5 valence electrons. And it does, right? Because it's hanging out in group 5a. So phosphorus having 5 valence electrons in group 5a, this is a thing that has been seen, hopefully. If not, now you know. So do notice that it's the highest value of N, even if I'm in 2 different subshells. So 3 is my highest value of N, so I get to count both the S and the P electrons for valence. The question was about the D subshell. I am not surprised. Let's do one that will make you angry. I don't mean that like make you angry. I mean that like let's do one that is not as straightforward. And I should say it like that because that's what I mean. Let's do chromium. Argon, chromium's down here. Argon for S1, because it's one of your exceptions, 3d5. You have 2 different values of N. You have 4 and you have 3. Only one of those is higher than the other, which is 4. So chromium has 1 valence electron. So it says 1 valence electron. Because it's the highest value of N. Highest value of N for your valence electrons. No matter what, every time. The highest value of N. And I know that's not what you want. I know you want it to be something different, but it's the highest value of N. We can do something interesting, but it's got to be weird, but I know how to draw it. I guess we can do iron again. I could do iron, do cobalt. Let's do rhodium. Rhodium doesn't get enough love. Rhodium, krypton, 5s2, 4d, 1, 2, 3, 4, 5, 6, 7. The highest value of N. 5 is bigger than 4. So rhodium has a grand total of 2 valence electrons. So this really is one of those times to essentially go back to the definition. So valence electrons are going to be the highest value of N. That's where our valence electrons come from. So that means most of your D block elements have 2 valence electrons, but not all of them, because there were 5 exceptions where they essentially steal an electron out of the S subshell to have either a half full or a full D subshell. Those 5 exceptions were chromium, molybdenum, copper, silver, and gold. Those are the ones that you are responsible for. I should say it like that, because there are some other exceptions, but the 5 you are responsible for are chromium, molybdenum, copper, silver, and gold. I'm also trying to do things like take small sips of my water, because I get reminded occasionally by my students that I write really fast. And I've always written really fast and I just forget. During lockdown, some of my colleagues also found out that I type pretty quickly. I know some of y'all can definitely out-type me, that's not a question, but if you put me against a random assortment of folks, I type either at the average speed of all of them or faster than some of them. And it doesn't hurt that I've been doing typing and occasionally writing in my free time. So I type pretty fast. No. Oh, not this thing. Sorry. Every once in a while, my computer and the Mac and OneNote don't always get along, but hopefully we'll hold up. Okay. What else can I do? Molecular versus formula mass. So there are a whole bunch of different words, and there are technically there are times when they mean there are times where you should use different words. I'm going to type them out and then talk about them. Molar mass, molecular mass, formula mass, molecular weight, formula weight. I think that's most of them. I'm gonna make them bigger because I know this is too small. Hey, don't do that. Don't do this to me. Just this little box. We're just gonna highlight the little box. Work with me today. There we go. Boom, bigger, there we go. So essentially, molecular mass and molecular weight should always be used with molecules, theoretically. So molecules are the things that have covalent bonds. So if we were really going to use this properly, I would never say molecular mass when I was talking about sodium chloride. Sodium chloride's ionic. It has no covalent bonds in it whatsoever. So if I want to talk about the mass of sodium chloride, and I don't just mean like a pile of salt in my hand, then I need one of these other ones. So usually like formula mass or formula weight are often then for compounds, which are also ionic, can also be covalent, but a lot of times we use molar mass because this is just generic. So the molar mass is the one that it's just any of them. Now the hard thing, to be honest, is that all 5 of these really are just interchangeable, because there are times where we should use one term over the other, but sometimes either we slip up and we mess up, or other times, because some of them are interchangeable no matter what, sometimes you just get kind of a roll of the dice. So all of these refer to the same thing, even though, again, there are times where we definitely should be using one over the other. And that is basically to talk about the mass of this as a whole, the atomic mass or grams per mole number of the whole thing. So sodium chloride, sodium. I have scribbled on this too much, unsurprisingly. Bring this back over here again. So all of these are going to refer to the same idea, which is if I have sodium chloride, my sodium, just way down here, is 22.99, and my chlorine which is over here, is 35.45, and I can add those together. And I do have my calculator with me. Shoo! Because you never really know what people are going to ask. 58.44. And this can be an AMUs because you could talk about one sodium ion and one chloride ion hanging out together. You could also talk about a whole bunch of these and deal in grams per mole. So, but they are essentially interchangeable. Again, there are certain times where you should use certain terms rather than others. But those, and I know it seems arbitrary to y'all, but those are kind of the picky details we usually don't ask about. Formula weight versus molecular weight versus formula mass. Also because, so I always stick molecular weight in here because in biochemistry, you usually ask about the molecular weight of proteins, even though a better term would still be molecular mass for that. But we're not going to have the weight versus mass discussion right now. But you'll oftentimes see these older terms hanging around in different fields, depending. But all 5 of these more or less mean the same thing. So speaking of a bunch of things that mean the same thing, let's stay in that vein and talk about electronegativity, polarity, and dipole moments. So now electronegativity is only one thing. That's pretty much it though. So electronegativity is a trend. And essentially fluorine is most electronegative and everything else basically kind of points towards fluorine. So it's very similar to electron affinity. The other thing I will tell you is because oxygen is so small, so its fluorine is by far the most, then oxygen, then chlorine. This doesn't come up often, but the fact that oxygen is more electronegative than chlorine is useful for various reasons to know. So I will state it now. We might bring it back later. I'm not sure. I have not been given the exam questions yet. So electronegativity is a trend. So we usually, when we talk about electronegativity, we usually talk about this atom versus that atom, and which one is more electronegative than the other. So when we talk about electronegativity, we're usually talking about individual atoms. Now then, the other terms. So I'm going to include differences in electronegativity. I'm going to include the word polar, write this correctly, there we go, polar and nonpolar. I'm going to include dipole or dipole moment. I'm going to include partial charges. I'm also going to include percent ionic character. These, remember, I don't know if you remember, but my segue into this topic was speaking of a whole bunch of words that all refer to the same thing. These are all going to be talking about the same idea. Now, there are differences in here. So there are different contexts in which we would use these, but overall, this is going to refer to the same general idea, which is the fact that when you are talking about elements and atoms and molecules and things connected to other things, you have a couple of options. But either you have perfect sharing of the electrons, perfect sharing of electrons We refer to this, by the way, as nonpolar or a nonpolar bond. Or you have uneven sharing. Of electrons. We refer to this as a polar bond. So the notion here, and there's various pictures that we can use, but essentially, if I was trying to think about the electron cloud that's going to be around this molecule, if I have two hydrogens here together, the electron density should be completely evenly distributed in between the two hydrogens. Neither hydrogen wants those electrons more than the other. Both of those hydrogens are going to basically be hanging out with their covalent bonds nice and evenly distributed. The two fluorines, on the other hand, are going to, or the hydrogen with the fluorine, not the same thing. It's going to look different. That fluorine, greater electronegativity, greater electron affinity, is going to want those electrons to come towards it. So you're going to see more of that electron cloud where the fluorine is. So fluorine is going to have more of the electron density. It just is. It still has a bond to the hydrogen. So the hydrogen is still connected to the fluorine, but much more of that electron density is going to be on or around the fluorine. That's going to give us uneven sharing or a polar bond. So that's the concept. That's the concept. Some other terms we can use. We could use things like greatest or least difference in electronegativity, where the greater, I should write this closer to where my examples are. Hold on. So a polar bond is going to have a greater difference in electronegativity. My fluorine is very electronegative. My hydrogen is not very electronegative. So it's a big difference in between the two of them. I have two hydrogens that are exactly the same, no difference in between them. This would be the same if I had two fluorines together, by the way. Even though fluorine is very electronegative, if it's the same element, the difference in electronegativity between two fluorines is 0, because it's the exact same atom. So we talked about differences, polar versus nonpolar. So polar is uneven sharing. Nonpolar is perfect sharing. Dipole moment, you're only going to see a dipole with something that's polar, but essentially what we can do is to demonstrate this change, we can draw an arrow. So we are actually drawing a dipole moment where you essentially have this like positive sign towards the thing that's not able to hold on to its electrons very well, and you point to the side where there should be more negative stuff. So there should be more negative stuff, greater electron density. Greater electron density towards the fluorine. Since you also have, so this arrow thing, this is a dipole. That's what the arrow thing means. So the arrow thing is a dipole or dipole moment. That is what that is. Partial charges, because we've got more electron density towards the fluorine, that also means that I could basically draw this symbol for the fluorine and this symbol towards the hydrogen. Basically, this is our way of demonstrating that this is a partial or part. So this is not a whole charge. So fluorine does not just get a negative sign by it. It's not the fluoride ion. This is hydrogen fluoride. This is a covalent molecule. And we expect, therefore, that covalent bond to mean that we don't just have a positive and a negative. We've got more negative stuff. So it's part of the charge, but not a whole charge on both sides. But since fluorine is always more electronegative than the hydrogen, the fluorine side will always be more negative than the hydrogen side. So we can still put these partial charges because they'll always be there, but they're not whole charges, they're partial charges. Then I went ahead and threw percent ionic character in there, just because the rest of these are all about covalent things. So all of these have to refer to covalent molecules and covalent bonds. That's the only time you get to really talk about those. But every once in a while, somebody is like, but I mean, if you have partial charges, then couldn't we rank something and be like, this one's got perfect sharing, and this one's got some difference between it, and then like sodium chloride, like those are whole charges. And if we wanted to stick an ionic something on this scale, we therefore need a term that we can use that would include an ionic bond, that would include whole charges, because everything else that we have is very specific to covalent bonds, is very specific to some kind of sharing. Ionic doesn't share at all. So if we wanted to put an ionic bond on this scale, we need something different. And then we use percent ionic character, where essentially we have a scale and we would just say that this is low to no ionic character, and this is high ionic character. So every once in a while someone's like, but couldn't we just throw something ionic on there? And if we were going to throw ionic on there, then we typically use percent ionic character so that we don't misspeak and use our terms properly. Because you wouldn't use partial charges with ionic compounds. Ionic compounds have whole charges. You wouldn't use a dipole or a dipole moment because, again, you have point charges. You have whole charges. They're not, sodium and chloride are not little magnets. They don't have a positive end and a negative end. There's just a positive thing and a negative thing. So different terminologies for different pieces. I promised y'all Lewis structures. I haven't gotten there yet, did I? Really thought I was going to get through these faster. Why do I always think that? But we talked about electronegativity now. And I talked about electronegativity, polarity, dipoles. So let's go ahead and do some Lewis structures. Let's see if I can talk about best Lewis structures and polyatomic ions and resonance. Let's do that. Let's walk through. Now this is going to take me a minute. This is going to take me a minute. But what we're going to do is we're going to go ahead and draw the Lewis structure for phosphate. It's an example that I do out of my notes if I have time in class. Otherwise, I threw it on the workshop. So, phosphate. So first of all, when it comes to Lewis structures, there is a set of steps that we're going to use. I assume Dr. Diekman came up with these because it would be a Dr. Diekman thing to have a like, this is the way that we will always do things, and this is the order. But I don't actually know that. I just know that when I joined the team, I was given notes and they had these instructions in them, and I like them very much. This is going to let us work through a lot of these things. So the first thing we're going to do, step one, count the number of valence electrons for all the atoms. And there's steps for dealing with negative charges and positive charges. If I want valence electrons, I would like a periodic table. I just copied and pasted something different, so I do have to go back and grab my periodic table. But hey, there it is. So go over there. Okay, so I have phosphorus and I have oxygen. Phosphorus is in 5A, oxygen's in 6A. So I have 1 phosphorus, that's 5 valence electrons. Plus I have 4 oxygens at 6 valence electrons each. Plus I'm going to add 1 electron for each negative charge. This is a -3 charge, therefore I'm going to add 3 more electrons. I'm going to add these up with my calculator because I don't want to mess up. 32, valence electrons. Arrange the atoms. Least electronegative atom usually goes in the center. It's best at sharing. Oxygen is closer to fluorine than phosphorus, so oxygen's gonna be more electronegative. Also, we usually like symmetry, so phosphorus being in the middle was probably gonna happen. So now I do need to come down here to get myself some space. I'm not gonna forget the fact that I had 32 valence electrons. 1, 2, 3, 4. Arrange the atoms. So I did this, I got 32. I arranged the atoms, boom. Connect all the atoms by single bonds. This should hopefully make sense because this is a molecule and we're trying to draw a Lewis structure, so we've got to connect everything together. You have to. 2, 4, 6, 8. Every line is 2 electrons. So that was 8 electrons. I should hopefully have 24 left over. Yay, good. Now that I have 24 left over, everything's connected. Now what? Complete octets for outermost atoms using electron pairs. Cool. 24, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Mount. So right now, I've got some instructions that says if I have extra electrons, I could add them to the central atom. Cool. But I don't have any extra. If I'm short of electrons, I could form multiple bonds. I'm not short of any though. Oh, let's double check. I haven't actually done that yet. If I was finished, I'm going to throw these brackets up before I forget. So I apologize that I'm not finished yet, but I'm going to put the brackets and the charge on the outside so I don't forget to do that. All of my oxygens look the same. So I can take any one of these and I can count in here. This oxygen is sharing 2 electrons with phosphorus, and then it's got 3 sets of lone pairs. So this is 2, 4, 6, and 8 electrons. So this is 8 electrons, 2 shared, and a bond, 6 as lone pairs for my oxygen. My phosphorus has also 8 electrons. So this has 8 electrons, so I have fulfilled the octet. I have 8 in bonds. So there's my Lewis structure. Now I'm not done yet for oh so many reasons. Now, things that we did do. This structure has the correct number of valence electrons. I'm not going to go back through and count them, but that's actually why we kept track over here on the right, is because I have assigned all of my electrons. And I have also completed all of my octets for everything. So everything right now has 8 electrons and only 8. This follows the octet rule beautifully. It's wonderful. But one of the questions that was asked was about best Lewis structure. Anytime you see best Lewis structure, that's a hint that we actually care about this last thing right here. The Lewis structure with the lowest formal charge is the most stable and preferred, which would be the best one, which means I have to actually do formal charge. So best is going to basically be your magical word to remember to do formal charge. When we do, not formula charge, formal, the word is formal. Formal, like it's in a tuxedo for some reason, or a beautiful ball gown, or something, nice pantsuit, formal. Suddenly my brain is trying to dress up elements in evening wear, which is very amusing, but not helpful right now. So formal charge, what we did when we made this molecule is we basically took all of the valence electrons and we just assigned them to be in places. That's what we did. So what we need to do is figure out how good of a job did we do on that. So what I'm going to do, and you still might notice I still have an oxygen versus a phosphorus because all the oxygens look the same, but we're going to analyze these. So what I'm going to do is I'm going to look at the total number of valence electrons on my oxygen, which is still 6, didn't change. But if I forgot, I can go back to the periodic table. So, and then I'm going to subtract the number of sticks. So this is valence minus sticks, what it brought minus sticks minus dots. Or what this really is this bond here. Well, really what we're doing is we're taking this bond, and the bond that's right here, we are basically now assuming that this bond that is made up of 2 electrons, we are also saying, all right, I'm going to give 1 electron to the oxygen, and I'm going to give 1 of these electrons to the phosphorus. So even though that this, when we did octet rule, we counted the 2 electrons for each of them because it is a shared bond. When we go to formal charge is about essentially dividing the electrons between all of the atoms. If making the covalent bond was like a marriage, then formal charge is a divorce, where we split everything back up again. We're not sharing anymore. So there's different formulas to think about when we think about formal charge. So a PLTL leader taught me what it brought minus sticks minus dots. This is also your valence electrons minus, technically this is half of the bonding electrons or bonded electrons. Again, there's 2 electrons in the bond. You only count 1 of them. Minus dots, or minus all of your non-bonded electrons. For oxygen, that's 1, 2, 3, 4, 5, 6. So this oxygen, all the oxygens actually have a -1 formal charge on oxygen. So sorry that formula looks weird because there's 2 different formulas in there. Yeah, I'll just say that apology and move forward. And if you have questions about it, we can always circle back. Phosphorus, how's the phosphorus doing? Well, phosphorus started off with 5 valence electrons. And then it is sharing 8 electrons. Again, we're only going to be counting half of the electrons in every bond for it. So we're only going to count 4. So 4 sticks, or half of all of the electrons in bonds around the phosphorus. It doesn't have any lone pairs, so none of those count. Gets me a +1. Now, this is a problem because I have both a -1 formal charge and a +1 formal charge. Whenever this happens, this typically means I can do better. It's not what it always means, but it often means. If you have both positive and negative formal charge, try to share more. Now, try to share more. Now, I have scribbled all over this, so I'm going to redraw this exactly as it is, but I'm just going to redraw this so that we can have a conversation about it without my color coding. So my first goal is to just redraw exactly what we have as it is so that we can have a conversation about it. I should still have my -3 charge. Everything should still just have 2 dots. So basically, this positive and negative business means that I could potentially share more. So what I want to do is I basically want to move one of my lone pairs off of an oxygen to share it with the sulfur, or phosphorus, to share it with the phosphorus. So when I do that, is part of the reason why either digitally writing is better, because that little tapping sound is much easier. Here's my new thing, sharing some electrons. I got a double bond here now. So now one of the things I want to double check before I do anything else is my phosphorus here now has 10 electrons. I know it's one of the other questions. So this is now sharing 10 electrons. Phosphorus. Let's go take a look at where phosphorus is on the periodic table and make sure that we're allowed to do that. There's phosphorus. Phosphorus is in period 3. Whenever you are in period 3 and below, you don't have to, but you can have an expanded octet. Expanded octet, so more than 8. They can basically break the octet rule with more. And that's what we've done here. Because we're in period 3, we are allowed to do that. Please note that if my central atom had been carbon or nitrogen, we would basically have to back up and be like, oh, no expanded octet for carbon or nitrogen or oxygen or fluorine. So can't do it. But we have phosphorus. Phosphorus can have an expanded octet, so we are good to go. So this thing I drew that has sharing 10, this is the period 3 and below is allowed. I am sorry for the coughing. Ooh, is this a cough drop? Oh, I'm at my husband's desk. Oh, thank God. So I was explaining to some of the people from the living learning community that we are not super, what's it called, neat. We're clean, but we're kind of cluttered folks in this house, which means since I'm on my partner's desk, the odds that there are cough drops within arm's reach is actually very high. Because I don't know when's the last time he had a cold, but odds are good that they stayed on his desk instead of getting put back in a medicine cabinet where they should go. It works for us. Okay. I don't know which is better, me coughing or me talking around a cough drop, but you don't get to decide. I do. Okay. So this is allowed. Now what we want to do is analyze this. Is this actually better? We made a change. Is this actually a better change? So this oxygen is still going to look the same as it did before. 6 valence electrons, -1 stick, -6 dots for a -1. My phosphorus now has 5 valence electrons, is now sharing 10 electrons, so -5. Still doesn't have any lone pairs. So my phosphorus is now 0. Ooh, better. We like it. Oxygen, on the one that changed, 6 valence electrons, -2 sticks, -4 dots, is also now 0. So this looks way better. I don't have a positive and a negative anymore. And what I do have is I have zeros finally. Now I know I still have 2 other oxygens that look like the -1. So I do have 3 oxygens with a -1 formal charge. Because my overall structure has a -3 formal charge, I'm never going to get rid of those entirely. But I have zeros now, which means this is way better. I know some of you then are curious about, well, what if we went one more? And what if we made another double bond? So I'm going to go ahead and take a look at that relatively quickly. And all I'm really going to do is take a look at the phosphorus. But the beautiful thing is, whenever you think, but hey, what if I changed something else? What if I can I do even better? The answer is, well, then build it and see what it looks like. So if the question ever is, well, could I do better? By all means, try to make it better, see what it looks like. This is still 6. minus 1 minus 6, which is -1. So I've got 2 of those. My phosphorus now is 5 minus 1, 2, 3, 4, 5, 6, which is -1. And these guys, 6 minus 2 minus 4. So the hard thing with this structure that I realized I scribbled all over, it has 2 double bonds, it has 2 single bonds. Now I have a new problem to decide between, which is the new one also has 2 zeros and 3 -1s. The difference is now I have a -1 on the phosphorus, and before I had a -1 only on oxygen. So if the question is -1 formal charge, I can either have it on 3 oxygens, or I can have it on 2 oxygens and 1 phosphorus. Which one do I want? And the better question is, how do we know? What do I actually want, and how do I know? Who is surprised that I'm going back to a periodic table? Back to the periodic table, my friends. This is now a question of electronegativity. The question is, which element is more likely to carry a negative formal charge? Which one's more likely to want more electrons? And that one's going to be the one that's typically more stable. So here's fluorine, the most electronegative atom that we have. And then here's oxygen, and here's phosphorus. Oxygen is much closer to fluorine than phosphorus. Oxygen is more electronegative. Oxygen is going to be better able then, as a more electronegative element, to handle the negative formal charge. So my more electronegative element gets the negative formal charge. That's oxygen. So I want the 3 oxygens to have my negative formal charge. That's how I know. So I don't pick randomly. I don't stop until I think it looks cool. I take the one that has whichever structure gives me, whichever structure minimizes positives and negatives, and then whichever one gets me negative stuff on the most electronegative element, or conversely, positive stuff on the least electronegative, if that's the direction we're going, lets me know. Okay, we've recovered. So all of that being said, this structure where I had a 0 on my phosphorus is the best structure. I know it's the best structure because of formal charge. Formal charge is how I know. Now, I'm actually not finished with talking about this structure, but I have been talking for almost an hour straight, which was probably not a good plan. So the next thing I do want to talk about before our time is up is resonance, which the structure will let me do. But first, I'm actually going to go ahead and take some questions. So I'm not ready for them yet, but if you, my wonderful, fabulous folks that get to look at the questions, if you will start to grab your questions, I will find myself some space.
Yeah, there's so many questions again.
I bet there are. You know, the other reason why there's so many questions is I warned
That's
those
true.
fabulous people that I was like, this is the second exam, and sometimes the second exam is light on questions. Not always, but sometimes. Because we've got a lot of like new folks in the living learning community with me in these reviews, which is awesome, by the way. Because it means that things are running surprisingly smoothly, because hopefully y'all had no idea. So I was like, just FYI, sometimes exam 2 is light on questions. And I'm like, oh, and now that I've warned you, that won't happen at all. So good to know it's working just like it should. Okay, I got some blank space whenever you're ready.
Yep. So could you explain B and BE exceptions, please? Would we need to memorize the charges for iron, cobalt, nickel, zinc, magnesium, the whole third block transition metals? Do we need to memorize any organic, inorganic compounds such as ethanol or anything? For covalent compounds, if you are just given 2 elements, how do you know how many there are of each metal? Can you explain ionic character? Can you explain what the exceptions are? For instance, you mentioned chromium. What did you mean by that? The professor just mentioned all of them. I'm sorry. Can you make a video going over the questions 3, 8, 21, 22, 26 from the fall 2022 exam? Would a compound like HCl and HF be covalent or ionic? Can you go over the expanded octal rule? Where does it start? Does the process of drawing Lewis structure differ between ionic and covalent compounds?
Okay.
That's it.
Awesome. Okay. So back to that comment that I had made where I talked for an hour straight, which is probably a bad idea. So a couple of things I think happened. So I think that I have already talked about the expanded octet, because that was that third period and below. What is happening there, by the way, is in that third period and below, what we're getting is in the expanded octet is you're finally getting elements that have access to d orbitals. So that quick reminder, which is that when n equals 3, I have 3 values of L equals 0, L equals 1, and L equals 2. So even if I don't have electrons in the d orbitals, it's when n is equal to 3 in that third period and below that I finally have d orbitals to access. So phosphorus and sulfur and chlorine, all of those have d orbitals, and so they can have expanded octets because basically they can be sharing electrons in their d orbitals. That's how that one works. So I admit that I didn't actually explain why that works. It's because of d orbitals. That's why it's the n equals 3 and not earlier. Yes, I can absolutely make a video that goes over all of these. Not a problem. Also good memory that I will do that afterwards. For those of you that may have forgotten, I'm happy to go over exam questions from the fall 22 exam, but I do this in a follow-up video because in the case that people haven't gotten to look at it yet, I don't want that to be spoiled for them essentially. Because I know like when it's live, like you're like, I want to tune into this. So I'm happy to do those, but fall 22 exams will do in a follow-up video instead. Okay, so Lewis structures for ionic things. And there's a reason why I basically just wrote drawing Lewis and ionic, because there are 2 different things. There are Lewis dot symbols and there are Lewis dot structures. And I am so sorry about this thing. So Lewis dot structures are the things where you have like whole molecules and you have to be like, all right, carbon's got 4 valence electrons, Hydrogen, there's 4 of them with 1 valence electron each. That's a grand total of 8. Work with me here, Pin. Symmetry is preferred. Also, hydrogens have got to go on the outside and everything's got to be bonded. 2, 4, 6, 8 minus 8, that's 0. So this is so Lewis structures multiple nonmetals together. So Lewis dot structures multiple atoms. Lewis dot structures will not be for ionic. Lewis dot structures will only be for molecular molecules. Lewis dot symbols, on the other hand, Lewis dot symbols really just show valence electrons. So a Lewis dot symbol, I could say, so we had carbon, and I apologize, I didn't flip back to my periodic table. Here's carbon in group 4A. So carbon and 1, 2, 3, 4 valence electrons for a Lewis dot symbol. But I could also do, I'm gonna grab one, lithium. And I can still draw a Lewis dot symbol for a metal, because a Lewis dot symbol is really only displaying the valence electrons. So Lewis dot symbols I can do with metals, or I can do them with nonmetals, because these are going to be for atoms or monatomic. Come on, or monatomic ions. Mono just means one. So by saying monatomic, I mean not polyatomic. Poly means many atoms together. Monoatomic just means one atom. So monatomic ions, just one by itself. So like I could do lithium plus is weird. I could do carbon 4 minus as a Lewis dot symbol. And basically it's got 4 valence electrons already. I add 4 more to it and I get it a charge. So as far as this goes, ionic structures with Lewis dot structures, not so much. Metals with Lewis dot symbols, yeah, we can do that. That's definitely doable. HCl, is it covalent or ionic? HCl is covalent, I promise. Now, I say it like this because there is a bond between the hydrogen and the chlorine. It is an ionic bond, I promise. Now, something really unfortunate happens, which is that usually you see HCl in 2 different contexts. You either see it as a gas or you see it in aqueous. Aqueous means in water. So the G here means gas. The AQ here means aqueous, which is specifically in water. Think like Aquaman. Now, if it's an aqueous, we call it something that might be familiar to you. If it's aqueous, we call this hydrochloric acid. So if it's aqueous, we refer to it as hydrochloric acid. Hydro for the hydrogen, chloric for the chlorine, acid for the aqueous, honestly. So you're actually basically naming each part of this individually. Since somebody else asked, I'm actually going to take a moment to point out the fact that this is also technically a binary acid because it's got hydrogen and one other thing. So if I wanted something else, what else would make any sense? Let's do do hydrogen and selenium. That'll be weird. Let's do that. I can also do this one. Aqueous. And then it would be hydro for the hydrogen, selen something for the selenium, ic acid for the aqueous. Now here's the weird thing. These things go together as if hydrogen was positively charged. Hydrogen's weird. It's also strange because it's like everywhere. So you would think if something was super common, it would be normal. It's not true. Hydrogen's everywhere. It's actually kind of strange. By the way, water. Water is also really strange, but it's everywhere. So we also tend to use it as a standard for a lot of things because it's everywhere, but water is really not very normal when you compare it to other things like it. Anyway, rant over. The question is this compound covalent or ionic? And some of you are like, but it's two nonmetals, it's obviously covalent. And that's true. But the person who asked probably looked at the fact that if you were to name this thing as a gas, we refer to this as hydrogen chloride. And that's its name. Like it was a metal and a non-metal. Hydrogen can only form one bond. Is one bond only. And because of that fact, it often acts as if it was a metal. And there's a reason why we stick it over in group 1A with the other alkali metals. So oftentimes we treat hydrogen, and we even name compounds as if hydrogen was a metal. It's not. Hydrogen's a non-metal. It really is blue here for a reason. I know my Microsoft OneNote's not happy with me. We'll see if I can make it happy. So hydrogen is blue. It's a non-metal. It really truly is. But it also is hanging out in group 1A, and it does often act as if it had a positive 1 charge. But it really honestly is two nonmetals together. So it's a covalent compound that we name as if it was ionic. Yay. Also, I have to shut down OneNote real quick. This will not take very long, by the way. What we're going to do is that. Just in case you're curious, I actually restart my entire laptop before I get on here, just so that hopefully does not happen. But it does. That's okay. Yeah, so the person who asked this, I totally understand. This is one of those weird things where hydrogen can act as if it was a metal, and therefore we name it as if it was one, even though it's not. Hydrogen's a non-metal. Okay, so we talked about drawing Lewis structures for ionic compounds, which we don't do, but we can draw Lewis dot symbols for metals. That's a thing. HCl is in fact covalent. We can name the gaseous version like it was ionic. Sorry about that. I think someone pointed this out, that there are exceptions. If you really do want more information about those exceptions, one, it's chromium, molybdenum, MO, and then copper, silver, and gold. And that's back in chapter 4. So do go back through your chapter 4 notes. These were exceptions in electron configuration. And I know that that was a while ago. We haven't practiced that in a long time. So do go back and see if you can find that information. If not, either shoot me an email or I have office hours or what have you. But there were just some exceptions to electron configuration. I think I probably covered them the Monday or Wednesday before exam 1. So trying to think back to where that would be in your notes. It actually would have been before exam 1 or on exam 1 is where that would have been. Basically going backwards a little bit, ionic character. So ionic character really is trying to put more emphasis on the idea of polarity, but ionic character really just lets us put an ionic bond on the scale. So whereas a lot of times when we think about polarity, we often basically have nonpolar to polar, and that's my scale from nonpolar to polar, and things can be more polar or less polar than each other. Percent ionic character really just lets me put ionic compounds on the scale. So then instead of the top part of my scale being polar, which is still a covalent bond, I can basically go one farther and I can put ionic bonds on it instead. So the idea is very, very similar. It's just thinking about like, how far are you willing to go? So when I think about this, I often think about things like, a lot of times when we give examples for like the real world around us, you tend to pick a scale, right? So you tend to pick like a distance, and you tend to pick either like where you live, but where you live could be like your dorm room or your house, or it could be the city that you live in, or it could be the state, or it could be the country, or it could be the earth. So essentially, this polar to nonpolar is more like the city or county, and percent ionic character is like the state. It just gives you a bigger range of things to consider. Hopefully that helps. Uh-oh. Oh, yes, I didn't lose it. Okay, percent ionic character. Yay. There were some specific questions about stuff to memorize. I do want to address those before I go back to resonance examples. Excuse me. So the question was, do we need to memorize the third block, like the options for charges in the D block? So the only things you really have to memorize are the charges for alkali metals, the charges for alkaline earth metals, the fact that silver is +1, that's a D block, and a transition metal, the fact that cadmium and zinc are +2, those are also in your D block. We can argue about whether they're transition metals or not, and aluminum's +3. Now there's one more piece which I left off, is mercury. It's down there. Mercury. Where's my little chart of polyatomic ions? To chapter 5. I think it's here. Chapter 5. So, oh look, subtitles again. Stop it. So mercury, there are 2 versions of mercury, but the one that you do need to know, there's mercury 1, which basically is 2 atoms of mercury together with a +2 charge. It's on your polyatomic ions list, though. So the question is about, what about some of the variable charges that are also in the D block? Here's the deal. You are responsible for your polyatomic ions. You need to know what these are. So the thing is, you shouldn't need to memorize any of the charges in the rest of the D block, because if I need to know what the charge is, I should be able to figure it out. I'll give you an example. Over here. Oops, I don't want my periodic table though. I should be able to figure this out. But this is the part where you're not going to like it. Let's go back to iron. So granted, this would actually have, so either it would look like this. Iron, we'll do 95. So my compound might look like this, and I need to name this. Now, what I really need to do is I need to know what I want. Yeah, we're gonna leave it like that. Don't change it. I Now, technically what I need to know is my iron has some charge, but I don't know what that is. I'm supposed to know what the nitrate is. So this is NO3 with a negative sign. This is nitrate. I'm supposed to know that. That's in the polyatomic ions list. That is a thing that I have committed to memory because it's hanging out in the polyatomic ions list. So, whoops, wrong thing. Those are just your room assignments, by the way. Don't get excited. I think I mentioned that I restart my computer before the review starts. That's also so that if I have any information on your exam up in a document, I close it before I start. So you can see all of my tabs. They might have a recipe of something I'm going to cook this week. They have nothing to do with your exam. So I'm supposed to know the nitrate, and I'm supposed to know the charge on the nitrate. So since I know that the nitrate's -1 and that this compound overall is neutral, because it's an ionic compound, it's going to be neutral overall. It took 3 nitrates to make it neutral. So 3 nitrates to be neutral, which means my iron has to be +3. So I can then name this. This is iron 3 nitrate. Now, this example is a little bit more straightforward because you could probably take a guess and be like, 3 is weird. It's either iron 3+ or it's iron 6+ or iron 9+, and 3 seems more reasonable. This gets a little trickier if we do something like this. Now there's no subscripts except for the one on the oxygen. Same game though. CO3, this thing is carbonate. I'm supposed to have memorized that carbonate has a -2 charge. So therefore, since there's only one carbonate, and it's got a -2 charge, the whole thing is neutral. This has to be cobalt 2 carbonate. So way back when somebody asked, how could we be asked about polyatomic ions? Like this. If you don't know what the charge is on the polyatomic ion, you'll get the Roman numeral incorrect. You got to know what the charge is on the polyatomic ion. Okay. Things to memorize. Organic, inorganic. Here's my general rule of thumb. I think I actually went through these for my class because I get this question a lot. Okay. Common names. Water and ammonia, things in green. There are other common names. Your textbook thinks that you will know what these are. We don't think you're going to know what phosphine is. It's too bad because phosphine is kind of cool. But ammonia, which is window cleaner, and water, H2O, we do think you know those two. So NH3 for ammonia with IA on the end is different from your polyatomic ion, which is the ammonium ion. I am so sorry about that. But they're related. Prefixes, you do need to know. That's a thing. Not to memorize the organic stuff. Methane, ethane, propane, butane, pentane, hexane. No one cares. Well, actually, correction. I leave these in here because if you go and buy a tank of propane, propane is the actual correct name. But if you go into organic, you'll get to mess with these. If you don't go into organic, you don't have to memorize this. The one thing I do like to point out is the carboxylic acid, because sometimes we do use that one. So COOH is one I recommend that you know, because sometimes we do use that one as a structural formula. So I would recommend carboxylic acid. The rest of these, not so much. And I think that's it in here. Yeah, there's polyatomic ion stuff. Yippee! So, 2 elements, how do you know how many of them there are? So The goal is to be neutral. Goal is neutral, which means if I have sodium with a +1 and chloride with a -1, a +1 plus a -1 is 0. So I just get to stick them together. Same game if I had a +2 calcium and a -2 sulfide. +2, -2, together, 0. They just go together. It's when they're not the same charge anymore that we have to do more work. So if I have something like magnesium, +2, by the way, I'm not pointing out all the times when they're in that the periodic table, so I apologize for that. Chloride, -1. Now I have to do some work here because my magnesium has a +2 charge. My chloride ion only has a -1 charge. So to make those balance out, this is basically +2 plus something times my -1 to equal 0. So I am in fact going to need that to be a 2 to make everything cancel out. So therefore this is MgCl2. Different things can help with this. The other thing, it's not my personal favorite, but some people like it, and if you like it, that's great, is your textbook does this thing that I think they refer to as the swap and drop, which is if I have a +2 calcium and I have a -3 phosphate anion, the 2 goes with the phosphate and the 3 goes with the calcium. So this is, I think they refer to it as the swap and drop. +2 calcium, then the 2 becomes a subscript on the phosphate. You do have to use parentheses. The phosphate's got the -3, the 3 then becomes the subscript on the calcium. Sorry, I'm trying to use my pen to gesture, and every once in a while I touch the tablet and it clicks my slide. So that's the other way I know how many goes with the thing. So we talked about the third period and below exceptions. We have not talked about boron and beryllium exceptions. I mentioned hydrogen, which technically is also an exception, that hydrogen only is one bond. Boron and beryllium are the other two main exceptions in Lewis structures. So boron and beryllium are Lewis structure exceptions. I have not gotten to this in my class yet. It's coming. I got time. So here's beryllium. Here's boron. Boron. We refer to boron as being naturally electron deficient. What do I mean by that? BF3, totally a compound. And it looks like this when you're done with it as a Lewis structure. And that's it. We'll go ahead and walk through that real quick. Boron, I scribbled over it. That was unfortunate. Boron has 3 valence electrons, 3 fluorines at 7 valence electrons each. That's 3 plus 21, which is 24. I connected everything by single bonds, so I used up 6. That gives me 18 left over. 2, 4, 6, 8, 10, 12, 14, 16, 18, minus 18. Done. And that's it. That's all. Boron, as you might notice, is only sharing 6. And that's fine. That's great. It's good. Because boron can do that. So that is its exception. Boron doesn't follow the octet rule. It is naturally electron deficient. Only does, it can actually do 8, so boron can do 8, but naturally just 6. So naturally electron deficient. Beryllium is actually going to have a very similar story to it. We usually draw beryllium chloride. Beryllium's weird for two reasons. One is a metal, but this is going to be a covalent compound. What's happening here is beryllium essentially is so small that the bonds that it forms with other things are better described as covalent, even though it's a metal. So we still are going to give this 2 valence electrons. 2 times chlorine is over here, 7. That's 2 plus 14, which is 16. So I'm going to put beryllium in the middle. Connect things together. I get 12 left over. 2, 4, 6, 8, 10, 12. Done. Beryllium just breaks all sorts of rules when it's a metal and it's got covalent bonds. That does happen though. That's real. This comes from studying beryllium compounds and studying how the bonds break and studying also what happens when you like have beryllium salts and you put them in water and you don't just get like positive like beryllium ions hanging out. You get beryllium to be a molecule and still hang out with the chlorines it came with. So this is a covalent molecule. Beryllium is satisfied by sharing a grand total of 4. So it also essentially breaks the octet rule. Beryllium breaks a lot of rules. And to be fair, boron's hanging out as a metalloid. So I mean, boron's also weird, but boron and beryllium are strange. They do have essentially their own what they're satisfied with. So I'm trying to not say they have their own octets because octet means 8. Neither one of them are an 8 thing. But they both have their own what they're satisfied by and what they're satisfied with. So they're unique. So those are the exceptions for boron and beryllium. Little red line, please go away. Yes, it went away. Hey, I got through all those. Wahahaha. Talk about that. Cool. So what I'm actually going to do is go back. I think I've talked about how polyatomic ions can be tested on the exam by now. Elements with more than 8 electrons did that. So we talked about the best Lewis structure because we talked about formal charge. We talked about Lewis structures in general. Important exceptions in Lewis structures, that was going to be my beryllium and boron. So hopefully that one's answered. Things I have not answered. I have not talked about percent composition, which is ironic because those are the 2 questions I came prepared with. But hey, I'm prepared with them. Those will just go in the follow-up video. I'm going to do resonance and bond order. Homonuclear things like ozone. I'm going to talk about that probably in a follow-up video if I don't have time. A coordinate covalent bond, which I'm going to run out of time. Honestly, the question about the 5 chlorines with iodine, I can try to draw that. I think that this was a question about expanded octets. I'm going to put that in a follow-up video, but it's also possible. I already answered your question. It's also possible I did not write down enough information and your question was more specific and I have messed that up. Naming acids, I technically already did binary acids, but I didn't do oxoacids and I didn't do hydrates. So in the 15 minutes I have though, let's do resonance. Also, I don't know if you guys heard the doorbell ring, but that means my groceries have arrived because there were only so many things I could do today and I splurged since I had the Gen Chem review and I'm doing grocery delivery. Okay, so it's now been like a half an hour at least since we did this example, but we were talking about phosphate like a half an hour ago. And we did Lewis structure, we did formal charge, and we landed with this phosphorus with 1 double bond, and the rest of them are single bonds. But And this is the best Lewis structure, but we didn't mention this weird thing, which is, what if I had instead put the double bond in a different place? Because basically this is going to be oxygen A, and this is going to be oxygen B, and this is going to be oxygen C, and this is going to be oxygen D. Those are all different oxygen atoms. I know they're all oxygen, but they're all different atoms. So what if I had drawn the double bond over here? And then this is a single bond, and this is a single bond. This is a single bond. So the only difference in between these two structures is the fact that I now have drawn my double bond. Whoopsies. All the Lewis dots still go in the molecule. The only difference should be now I have drawn the double bond in between phosphorus and a different oxygen. It was to the one on the top, oxygen A. Now it's to the one on the right, oxygen B. These are what we refer to, I'm going to draw the arrow in here before I forget. These are what we refer to as resonance structures. And as you might have already figured out, we're also not really done yet. Because that double bond could go anywhere. The other thing about this is because that double bond could go anywhere, that actually also means that it is everywhere. I'm not going to actually finish drawing these with all the dots, so I apologize, but I am just going to draw the general idea, which is, hey, my double bond can be in different places. So it could be at the top, that's 1. On the right, that's 2. On the bottom, that's 3. On the left, that's 4. There are 4 resonance structures. That's an exam question we like to ask, by the way. How many resonance structures does this thing have? We do draw them with the arrow in between. This is a double-headed arrow. That's the resonance arrow. And the thing about this is that in real life, this actually means that in real life, I would actually have this electron density ooched out over the entire molecule. So real life should be an average. Because if the structures I drew were real, with a double bond on the top or the side or the bottom, then essentially I would have a phosphate molecule where one bond was also shorter than all the others. And that's not true. When we get data for this, real life has all 4 bonds of the same length. And if they're all the same length, then this notion of what I drew with 1 double and 3 singles isn't right. So the reality is that they kind of average all out so that electron density is kind of ooched out over the entire molecule. This is the reason why we usually pair resonance structures, the 4 of these, with bond order. So I don't know where y'all are, but in my class, I always throw bond order up when I just say, hey, there's a single bond, a double bond, and a triple bond. Bond order, and we'll come back to it. For a single bond, bond order is 1. For double bond, bond order is 2. For a triple bond, bond order is 3. Now is the time we're actually going to use that, though, because what we're going to do is we really want the average. We want to describe real life. So when I look at my beautiful Lewis dot structure, what I see is I have 4 bonds total. And they are a single bond, another single bond, another single bond, and a double bond. So up here is the bond order of each bond. That gets me 5/4, or 1 1/4. And that's the bond order of a phosphate oxygen bond, of a phosphorus oxygen bond in phosphate. So I'm going to walk through that again. So we have our beautiful structures, double bond on top, or the side, or the bottom, or the other side. We really want to describe this what it is in real life, which is an average. In order to describe an average, I'm essentially going to take an average bond order. So this thing up here is going to be the average bond order. So it's the total number of bonds that I have. I have 4 bonds because I have a phosphorus to 4 different oxygens. So 1, 2, 3, 4 bonds total. And what I have is I have 3 of them are single bonds and 1 of them is a double bond. So 1 + 1 + 1 + 2. So each single bond gets 1, the double bond gets a 2. 1 + 1 + 1 + 2 is 5, divided by 4, or 1 1/4. And this is my average bond order, is 1 1/4. That's bond order. So bond order typically is described as going with resonance, because usually we want to talk about resonance. We want to talk about the fact that that double bond isn't really in one location, it's actually in all of the locations. So to do that, we either talk about resonance structures, or we can talk about how many resonance structures are there for the Lewis structure. And it's as many as you need to draw all of the options. So down below I had 4 resonance structures. Or sometimes we can also ask about bond order. So then in that case, we're asking, what's the average bond order of the phosphorus oxygen bond in phosphate? So that's what we were doing with all of this. Just taking a breath. Couple of things to note. I promise we will ask you something about resonance. I don't know if it's going to be about resonance or about bond order or about both, but we really like this question. So we're going to ask you this question. So that is the reason I wanted to make sure that I covered it, because it's going to come up. Granted, so are the math examples that I haven't gotten to talk about. And that was my choice, obviously. Also because oftentimes math is better to do in a video where you can stop it and replay as much as you'd like. I'm going to scroll back and see what's left. Okay, we talked about those things. We did resonance and bond order. Yay! Yes, I did abbreviate that BO. I did. Percent comp, got that. Oh. Homonuclear like ozone. So the thing I assumed that this was about, as far as homonuclear things go, I can't answer this question, I think. Here's the deal. There are some homonuclear things that you should know. I'll also be honest, I never know if these are going to show up on this exam or the next exam. So the person mentioned ozone. We actually don't assume you know what ozone is. So if you ever need, O3 as ozone, we'll just tell you that. We don't actually ever assume that you know that the word ozone is 3 oxygens bonded together. We'll tell you that one. So we don't actually ever assume that you know that ozone is O3. The thing we do assume that you know, we do actually assume that you know that hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, these guys, which I personally learned them in a different order. I learned them like this. I learned Brinkelhoff. I know some of these little twos there. All of these are what we refer to as homonuclear diatomics, which means that all of the oxygen that we breathe is actually O2. All of the hydrogen, if there was hydrogen that we also were breathing, it's pretty light, it floats up, so it's not as likely, is H2. All the nitrogen in our atmosphere, N2. All of these, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, naturally come paired. They naturally come as two of the same atom bonded together, which is part of why I didn't do it here, but we often do oxygen as an example, also because it lets us do the whole like 6 valence electrons times 2, which is 12, bond them together, 2, that gives me 10 left over, 2, 4, 6, 8, 10. Now I'm out of electrons, but I also have not completed my octet on the left, so I am just going to move one over for sharing. There you go. So oxygen naturally comes as a diatomic molecule, 2 atoms bonded together. In this case, with oxygen, it's a double bond. So some people learn that as like 7 star for the hydrogen, because you can form the number 7 on the periodic table. Also, it is 7 elements, 1, 2, 3, 4, 5, 6, 7. So some people learned it like that. I learned Brinkelhoff. It's also okay if you've never heard of this before. I talk to high school chemistry teachers every once in a while. And if they've got a nice mnemonic, I try to pick it up. Whatever helps. Whatever helps. Hey, I got one more question in there. Wahahaha. I really don't mind doing the follow-up videos. It's just if I can fit one more thing into 2 hours, I will. Okay. Cool. So before we log off, are there other questions from the chat that I can add to my list so I know what they are and so that everybody knows what else I'm going to be putting in that follow-up video?
Yeah, there are a couple of questions. So the first one is, can hydrogen have double, triple bonds in a Lewis structure? Okay. Are all binary acids covalent? Are acids just determined by H being in the front acting as a metal? Why HCl is not called hydrogen monochloride? Are we responsible for knowing how to work with 3 elements formed to make a compound? Can resonance structure have different formal charges? Can you go over bond strength and length in the follow-up video? How can homonuclear atoms be shown in an exam as a question?
Awesome. Okay, so knowing about 3 elements in one molecule, this really would be with polyatomic ions. That's really going to be the only way that you would know how many of anything there was, because I can't give you like carbon and oxygen and hydrogen and be like, tell me how many of each there are in a molecule, because there is essentially like an infinite or nearly infinite number of molecules that those 3 atoms can make. It's ridiculous. Pretty cool, actually. It's also the reason why organic chemistry is a 2-semester class all by itself, because there's a lot of options with those guys. But I can, back to like some of the examples we were doing polyatomic ions, like if I have like magnesium, which is +2, and I have sulfate, which is -2, those only go together in one way because magnesium is a good job, because magnesium is an alkaline earth metal, so it's got a +2 charge, and it always only has that +2 charge, and sulfate is a polyatomic ion, and it always has a -2 charge. So The hard thing is that how would you know how many of each element you have if there are 3 atoms, 3 different elements? It really depends on what those 3 elements are. But polyatomic ions is part of how you would know that. So back to how would you be tested on polyatomic ions? Like that. So I'm going to say that I answered this question. Bond strength and bond length, as the person mentioned, that is definitely going to be a follow-up video. Things I cannot do that in 30 seconds. Does hydrogen have double or triple bonds? No. No. Hydrogen, only one single bond. So technically hydrogen is also an exception to the octet rule. But hydrogen only has that poor little 1s electron. So hydrogen, only one single bond ever. I know there was a lot of other questions about binary acids and covalent and hydrogen chloride. Honestly, I will try to address that in the follow-up video. I think you guys are just mad that naming conventions are sometimes dumb. And I really honestly mean it like that. Like, there are things that we name and they do not make sense, but we have not changed it. So for those of you that are like, but I don't understand why HCl as a gas is called hydrogen chloride, I gotta go with it just is. And if you would like a better explanation, I recommend either Dr. Diekman or Dr. Seibert. I know Dr. Seibert's not teaching with us this semester, but he's the one that loves like the history of naming. I don't, because sometimes the history of naming is we just never changed it, which is dumb. But sometimes that's what we've got. So I'll try, but honestly, I think we're kind of at the point that like that it just is. It just is. Binary acids are covalent. Yes. Binary acids. If it's an acid, it's covalent. Resonance and formal charge, I'll try to address in the follow-up video, because basically the short version of this is if you draw it, should just go ahead and say this real quick. If you draw it, you are going to find the best structure, which means optimize for formal charge first. Then look for resonance. That being said, we as instructors on exams, we can give you things that are like, here are a bunch of resonance structures, and they might have different formal charges. But if you are supposed to find resonance, you are always going to do formal charge first. So you find the best structure with formal charge, being all as happy as it can be, then you look for resonance. Resonance is a more expanded concept, which is, I'll try to talk about that in a follow-up video. But if you are going to do it, and we ask you about it on an exam, you find the best Lewis structure first with formal charge, then look for resonance. I thought there was one more thing I could answer real fast. Oh, how are we going to ask you about the homonuclear diatomics in this exam? I honestly don't know. Sometimes my colleagues surprise me and they put it in. I honestly don't know how we would put that in this exam. I think it actually fits a lot better in later exams, but the definition of homonuclear diatomic goes in chapter 5. So maybe the person that wrote chapter 5 questions got really fascinated by the words homonuclear diatomic and thought you should know them. I don't know if you can see me shrug, but this shrug is not supposed to be sarcastic. It's really just an honest, like, I don't know what they've asked yet. I haven't seen your exam questions yet. Yay, I don't know. We'll go ahead and write this out since I've been saying this word out loud and I don't know how well the caption's been going. Homonuclear diatomic. This really is, homo means same, nuclear is for nucleus, which basically means it's the same element, same nucleus, same element. Di means two, atom. So literally the same element twice over is what that means. But yeah, I mean, so it could go on like a true-false question about homonuclear diatomics. It could be in one of that. You've seen those before. My AirPods just died. Yay, that's good. That must mean that we're out of time. And we are, because it's 6:05. So sorry I held you guys over, but we're done. We will see you all next time.
Thank you so much, Dr. Taylor. Thank you everyone who attended this evening. If you have any leftover questions, we will be recording these and sending these to Dr. Taylor again. I know she's went over quite a few of them at the end here, and those will be answered in another video. So thank you all so much. Have a great night.